Okay, I think this might be the last section. Logarithmic equations and applications. Again, you'll have everything you need to complete topic 6 homework and to prepare yourself for the quiz exam. So exam 3, you guys finished the rational. That was in the normal amount of time, and now logarithm is kind of being rushed. Exponents, logs, inverse functions. Started with the inverse functions, partially because logarithms and exponents are inverses of each other. And I know that Alex seemed to have started here, so you're going to have everything as you go through this. Let's do some solving. So we're going to solve logarithmic equations, and we're going to use logarithmic equations in applications. So there's a difference between these two equations. Log of the quantity 3x minus 4 minus log of the quantity x plus 1 is equal to log of 2. And log base 3 of the quantity x plus 6 minus log base 3 of the quantity x minus 2 is equal to 2. These are two very different, these use two very different techniques to solve these logarithmic equations. So, I don't know if they're very different, but they are different. So, let's first start with the first one and kind of go through that process. So here is the way we use this for solving equations of the first type. We're going to use the equivalence property of logarithmic expressions. Just like there was an equivalence property for exponential expressions, there must be one of logarithmics, because these two functions are direct inverses. So there has to be one. If there is one in one, it has to be in the other. So if b, x, and y are real numbers, again, b can't equal 1, and it has to be greater than 0. It has to be a positive value. Then the log of base b of x equal to the log base b of y means that x equals y. So that's just straight across. And that's really what we're going to use. The key here is that we have one log on this side and one log on this side. So we have to get them to that form, and then if they have the same base, then whatever's inside must equal whatever's inside the other one. So here we have log base b of the quantity 5x minus 1, and I don't know why the parentheses didn't show, but there should be parentheses here. Okay, equal to log base 2 of the quantity 2x plus 17. Because the log base 2, what we're really doing is saying, well, let's raise this. Let's put a 2 under here and a 2 under here. 2 log of 2 just becomes 1. This filters off. This filters off. Whatever you do to one side, you got to do the other. They basically filter off, and you end up with this idea. 5x minus 1 is equal to 2x plus 17. And we're trying to isolate, so I'm going to minus 2x from here, minus 2x. Now my x's are all together, that goes away, and I have 3x minus 1 is equal to 17. I'm going to add 1 and add 1. 3x is equal to 18. Divide by 3. Divide by 3. That becomes 1. So x is equal to 18 divided by 3 is 6. So x is equal to 6. We can actually consider this, right? If I plug 6 in for this x and 6 in for this x, what happens? Well, 5 times 6 is 30, minus 1 is 29. 2 times 6 is 12 plus 17, which is also 29. This had better be right. All right. Let's try another one. All right, here we're just using log. There's no base, so it's considered base 10. But I have a log here, and I have a log here. And I have a log on the other side of the equal sign. I can't combine these. I can't do that yet. I need to address the two logs on the left side. So I can write them as a single log. Again, the bases are the same. So we learned how to combine and write as a single log, and that's what we're going to do. I'm going to use and write log of, because this is subtraction, it becomes a division problem. So it's 3x minus 4 over x plus 1 is now equal to log of 2. Great. Now I have a single log on both sides, and they can filter off. It's kind of this idea I raised to the 10. So they filter off, they become 1, and I'm left with 3x minus 4 over x plus 1 is equal to 2. And this is a rational expression equal to a constant. So I'm trying to figure out what x is equal to, so I'm going to multiply the left side by x plus 1. And of course, if I multiply the left side, I have to multiply the right side. 1. This is over 1, and it's multiplying, so this cancels this. They filter off. I'm left with 3x minus 4 is equal to 2 times both terms, so 2x plus 2. And then, again, I want to isolate my x, so I'm going to minus 2x minus 2x. I'm just trying to get the x's on one side. Doesn't really matter which way I go, but in this case, it'll stay positive if I do this, so that goes away. This becomes 1x minus 4 is equal to 2. And then I'm going to add 4. So I end up that x is equal to 6. And we can kind of see that again. If I plug 6 in for x, up here I get 3 times 6, which is 18, minus 4 is 14. And then if I plug 6 here, I get 6 plus 1, which is 7. But remember, when I rewrite this, it's rewritten like this, where the log has this term above this term. Well, what's 14 over 7? 14 divided by 7 is 2. So this really, at this point, so this is the answer. And we can see it at this point here. This says log of 2 is equal to log of 2. Because this is 14 and this is 2. Or not 2, 7. Yeah. And 14 divided by 7 is 2. So, yeah. Pretty nice. You can usually check these in some way, something like this. All right, let's move on. Oh, nope, this one's yours. So combine it and then clean it up. Let's move on to the other method. If you can have questions, you guys know where to ask. Solve a logarithm of the other type. So this is where there's a mix of logarithms and constants. And just so we're clear, a constant doesn't necessarily mean a number. It can be a value that you know the answer to, or you know what it's possible to represent. So you collect all logarithms on one side, and then you rewrite the equation in exponential form. So, and I will talk about this. This idea is, let me write it out. So log of b of x is equal to k. And the cool thing is that these, because they're inverses of each other, and they're really complete, like the best types of inverses, this says our base of b raised to the power of k is equal to x. And you'll notice I did these as arrows going both ways, right? You can interchange between exponents and logarithms pretty consistently almost in every case, as long as you don't end up have two unknowns in weird places. So this is definitely your friend, this property, that shifting of them, and we're going to use that. That's one of the properties we're going to use here. All right, so we have, parentheses got missed again. Okay, so we have the log base 5 of the quantity 3x plus 1 is equal to 2. So again, I'm pulling everything down, and I'm crossing and crossing. So then I rewrite 5 to the power of 2 is equal to 3x plus 1. Well, we can, again, now we just keep the process of solving. 5 squared is 25, equal to 3x plus 1. We minus 1, minus 1. 24 is equal to 3x. Divide by 3, divide by 3. That filters. 24 divided by 3 is 8. So x equals 8. These are harder to plug back in. You should plug them back in because a big important process is that the argument can't be negative. So here this isn't going to be. 3 times 8 is 24, plus 1 is 25. So it's kind of like 5 to the power of 2 equals 25, which we know that's part of the process of solving. But you can't have the argument be negative. And the argument is what's in these parentheses. So this here in the parentheses is the argument. Many functions have arguments. That's just the formal name of them. And in logarithms, they cannot be negative. So you're definitely using that to our advantage to check our work. In this case, 8 won't make that negative, so we don't have to worry. Sometimes you'll get 2 answers because it's a quadratic or something and it gives you 2 answers. And you may have to throw one out if it makes the argument negative. It can be negative, but if it doesn't make the argument negative, it's still fine if it's negative. But if it ever makes the argument negative, then it won't work. Awesome. So here I have a log here, and I have a log over here, but I also have this constant. And I can't do anything with that. So I'm going to make the constant positive, bump it over, and I'm going to bring the logs all together. So first things first, let me add 3. And add 3. So now I have log of 4, x squared minus 9, and it's equal to log of 4, x plus 3, and plus 3. Well, now I'm going to minus log of 4 of x plus 3. And I got to minus it over here. 4 of x plus 3. So now I have log of 4 of x squared minus 9 minus log of 4 of x plus 3 equal to 3. Again, I need it in a single log on one side, so that's what I'm going for. I'm now going to take care of the subtraction and make it a division problem or a quotient. So it becomes 1 log base 4, and it becomes x squared minus 9 over x plus 3, all equal to 3. And actually, before I start working with this, I can simplify that. So why don't we do that? So what is x squared minus 9? X squared minus 9 is equivalently, my hope is you're remembering this from when we did quadratics. It is x and x, and the only way to get 9 that'll work is 3 and 3. One of them is a plus, and one of them is a subtraction. And then this is x plus 3. But we can see, whoops, don't forget the equal 3. This filters off. That's equivalently 1. 3 over 3 is 3, and a over a is, or 3 over 3 is 1, and a over a is 1. So x plus 3 over x plus 3, it's 1. So then this becomes log base 4 of x minus 3 is equal to 3. Well, now we're going to do the drop down and cross. So this becomes 4 to the 3rd power is equal to x plus, nope, that's not right. I don't know that I can fix that. Yeah, I'm going to try to. Eraser, that's not the eraser. Eraser, good. See if I can get the writing instrument back, and then write, and then ink. There we go. So x minus 3, and then I don't know if you know what 4 cubed is. 4 cubed is 64. It's basically 4 times 4 is 16 times another 4, which is 64. So 64 is equal to x minus 3. And again, we're trying to solve for x, so I'm going to add 3, add 3, and this becomes 67 is equal to x. Great. So then the question becomes, if I plug 67 in for x, will it at any point cause my argument to go negative? Here, they're just addition, so it won't. Here, I'm actually squaring 67, so it's a much bigger number, much bigger than 9, so it will stay positive as an argument. So that is indeed my solution. Let's see. Now one for you to do. Again, get your logs together first, and then combine them into a single log, and then convert it to exponents. Let's move on. Great. Let's use logarithmic equations in applications. So this has a try embedded. I'm going to go ahead and do this one. The following formula relates the energy, capital E, in joules released by a earthquake of magnitude capital M. And this is actually the accurate expression for magnitudes greater than 5. So the log of E is equal to 5.24 plus 1.44 times M. And again, the magnitude M must be greater than 5. So what is the energy released by a magnitude 6? And then you get to try a magnitude 7. So I'm going to do a magnitude 6, you try a magnitude 7, and we're actually looking for E. So that means we only have one log over here, but we don't have a single value, a constant yet, so we want to do that. But we know what capital M is. It's right here. For your try, it's going to be right there. So I'm going to do this one, and then you guys can do a try, and then we'll look at the other one, the next part of this. So log capital E is equal to 5.24 plus 1.44 times 6. I want to be clear, this isn't really crazy, right? So 1.44 times 6. You'll probably need to use your calculator, but that's fine. That becomes 8.64. Still 5.24 plus still log capital E. All right, we're going to add that to 5.24. 5.24. And that gives us that our log E is where I'm going to do the changing, is equal to 13.88. So I'm bringing down my base, and I'm crossing these. Remember, we do know our base. If it's not given, the base is 10. So 10 to the power of 13.88 is equal to E. So that is approximately holy cow. Well, that's a really, really, really big number. Okay. Wow. Yeah, let me give you the whole number. Let me give you so this is maybe I could let me do that. So I'm going to give it to you in scientific notation. It's one of those that's that big. So this is approximately, and maybe we'll do to 2 decimal places. 2 decimal? Yeah, let's do 2 decimal. So 7.59 times 10 to the 13th power. And if you don't remember scientific notation, that means move my decimal place 13 places that way, and that's how big that number is. Right? So written out, because that's going to be really hard to think about, this is 7, 5, 9, there, then 1, 2, 3, 4, 5, 6, 7, 8, 9. I think this is right. So 1, 2, 3, 4, 5, 6, 7, 8, Yep, one more, 13. So, let's see. What would that be? Let's try to put some commas in here. So there's the 100, this is the thousands, this is the millions, this is the billions, this is the trillions. So over 75 trillion joules of energy is released in a magnitude 6 earthquake. That's pretty massive. That's more than enough energy to run your house for the next 10 years. Genuinely, it's probably more than enough to run your house for the entire time that you live. As a comparison, and you guys get to try 7. So you guys get to try 7. I would write it like this just because it's easier, right? That's what we do with really big numbers or really small numbers. Small numbers usually have a negative exponent on their 10. As a comparison, a 1 megaton nuclear weapon would have an energy release of 4.18 times 10 to the 15 joules, which means it's still bigger than a magnitude 6. Okay? Way bigger than a magnitude 6 earthquake. My guess is it's probably going to be bigger than your magnitude 7, but I don't know. And the eruption of the volcano Krakatoa in 1883 produced an energy release of 2.09 times 10 to the 19th power joules. So much, much bigger. So this up here is a scale magnitude bigger than ours over here. And this is so ridiculously more, it's not even something we want to think about. That's the energy release. I will say that I don't know if it was this one. I don't think it was this one. There was a volcano erupt early in the 1900s in, I think it was in the Philippines, and it basically cooled the planet. So that earthquake, or that volcano erupting, put enough ash in the air that it cooled the planet and brought extended winters about the time Washington was crossing the Delaware. It didn't happen then. It had happened like 5 years earlier. But by the time all that ash distributed over the entire planet and brought cooling temperatures was why the Delaware froze to that level. So yes, pretty crazy. That's not something you'll be tested on. That's just being old and knowing lots of stuff. All right. There we go. And I think, we got to do modeling. I guess there will be another video. All right, let me end this and I'll get started on the next one.